a finite field to a 32-bit architecture, right? So before we go into it, I just feel like it might be good to go over a brief overview of the FRI protocol. I'm no expert, but this is just a high-level overview. So imagine you have a computation where you have memory trace. So you have memory, and then you have the addresses, so where that information is stored in memory. Can you see here?
Yeah.
And the values, right? So let's say we have at address 0, 1, 2, 3. We have values, let's say minus, for simplicity's sake, -2, -1, 1, and 2. What you basically do with, in the FRI protocol, you take the values of the memory and then you interpolate them into a polynomial. And how this works is basically you select something like a finite field, and then you create a graph of sorts, and then you take the points that the memory lies at. So let's say, I guess negative numbers aren't really properly parts of finite fields. In this case, this -2 would be 2 to the 31 minus 2. So it'd be some super high number, but for simplicity's sake, let's say it's just -2, -1, 1, and then 2. And then what you're going, oops, no, I made a mistake. These are the x coordinate is going to be the addresses. So
Okay.
2, 3, 4. And then the values are going to be -2. So you have down here, -2, -1. And then you have, at address 2, you have 1. And then,
Make it the size of
oh, you can't see in the back. Okay,
But
cool.
maybe change the marker as well. I don't think that one is very.
Okay, all right, gotcha. Will do. So we have,
I can graph it if you want.
does everybody kind of get the gist though? You basically just take the memory trace and then make it into a nice polynomial.
Yeah.
Is better?
Yes.
So you have at 0, 1, 2, and 3, you have the values -2. This is likely what it wouldn't look like actually on the curve, but just for the explanation, I think it's a good intuition. And then here you have 2, right? So you create this kind of like almost linear polynomial. And with this polynomial, what you're going to do with the FRI protocol is evaluate it at different points, right? So there's this thing called a fast Fourier transform, which is what the paper gets into. That is really important for these Starks to work. So first we have Starks and the FRI proof of proximity. This is basically, you take these points, interpolate them, and then they create something like a low degree polynomial. So we know that this polynomial right here is of low degree. So for example, let's say this right here is y equals x, right, to the first degree. We know it's low degree. But imagine if you got one of these values wrong. If you were doing a computational trace and you weren't able to actually replicate the computation, you would end up with a point right here. And what I'm going to do in red marker is an incorrect computational trace. So in order to interpolate this polynomial, you'd have to do something like this, right? Which is not correct. And in fact, it's not. We know that it's not correct because what it's going to produce is a high degree polynomial. So this is like, this looks like a cubed curve, right? So this might be x cubed. And the test here basically assures that whoever is creating this proof can create a low degree polynomial and not a high degree one. The reason why we want to use circle Starks is because historically, in order to do this in the FRI protocol, we have to use finite fields that are of a prime -1. Oops. I lost the eraser. Okay, cool. So the goal is to make it so that we can use this prime, but Starks before we're using this prime called the baby bear prime. And what you had to do is rather than take the word size of your computer architecture, for example, a 32-bit architecture with the Mersenne prime, in order to loop around, so you get to the highest value of the Mersenne prime and then you go back to 0, you take whenever the 32-bit register is turned on, you just turn that off and then turn the first register on. So it's very computationally effective. The baby bear though, you have to calculate this 2 to the 31 minus 2 to the 27. I don't know why these are calculating as subscripts. It should be superscripts. But it's really great for this architecture. And there was an attempt to do it where you basically map the finite field onto an elliptic curve, but now they're talking about mapping it onto a perfect circle. So why the need for circular fields? This part of the paper, I'm gonna be honest with y'all, I didn't really grasp it, but so the first one is that the chain of curves, right? So for pairings, you use different curves in order to maintain zero knowledge. But this one, you don't need a chain of curves because the squaring map is a quadratic degree and 2 to 1. So the quadratic degree part, what I got from it is that when you square a number in the finite field, then there's this mapping. And then after that, I don't really know what the mapping is used for. But apparently it makes it so that it's a much more simple curve or much more simple operations. And then the second one is that the FFT is efficient due to the polynomial basis. This was another, I don't have a math degree, I'm computer engineering degree, but I feel like this one was, so you have polynomial basis, which is how are you going to define the polynomial that you're creating these proofs on, right? It could be like a monovariate polynomial where you have just x, or it could be something like a bivariate polynomial where you have z equals, x, let's just do the circle, x squared plus y squared, right? That's what the circle is. So you have this bivariate field, or bivariate polynomial that you're working with. And then also simpler algebraic geometry compared to other crypto systems. So there was something about not using the Riemann-Roch theorem, which I didn't know much about, but apparently it's pretty simple because you're just using a circular curve. Yes, please.
I can try and add some insights. I'm also not a mathematician by training though, so this is pretty vague. But by using this circle basis, by mapping to the circle basis, you're basically taking a prime field and mapping it into a group whose order is the square of your field. So if your original prime is 2 to the 32 minus 1,
yeah,
then you're mapping it into a group which is 2 to the 64 minus 2 to the 33 plus 1, and that plus 1 at the end means that you have lots of roots of unity in this new group, which means that it's
the FFT works better.
Which means the FFT works.
Okay, thank you. Okay, so that was kind of the next part. We need the fast Fourier trace. So basically in the FRI protocol, we have like a lazy verifier, right? So the verifier only wants to evaluate, they don't want to evaluate a polynomial of like 40 degrees, right? Where we have something like, okay, I'm gonna write it in red because we don't wanna do this. Where you have something like z equals x to the 40 plus 7x to the 39, for example, right? It takes a lot of computation to do that. So what the protocol does is use a series of fast Fourier transforms, which is why they're so important to the protocol, to basically, it's called like a split and fold technique, where you use recursion to break down these large polynomials into smaller ones. Using recursion. So for example, this might be broken down at some point to like z equals x squared plus 7 or something. It's just a guess. But the verifier then says, okay, now I'll go ahead and evaluate this, use the number 3, and then get the value 16. Super easy versus doing all the computation for this large polynomial, right? And I think I bring that up a little bit. Okay, so this is the circle field. So this is the reason why they actually chose the circle field. I actually do want to stay on this point though. Hold on, let me switch. Okay, perfect. So as you can see, the FFT basis of the circle, an n-dimensional basis of polynomials which only depends on the size of the domain. So what I got from that is that the domain itself can be kind of like what Zach said. You can do FFTs very efficiently over this field. And this part right here, like this union equation, I know it's for defining the domain, but then there was a little bit of category theory that went into, at least I think this is category theory, that went into defining different domains. And this is another part of the paper that I had a lot of questions about, because I'm not sure if we're mapping to the different domains of the recursion steps of the fast Fourier transform. Because what you do is, as you're breaking down the polynomial, you're kind of shrinking or using sub fields of the extent of the domain. So this was another part that I've never really seen this domain notation. If you could maybe describe.
I'm afraid I've not read the paper. This is a little bit beyond my domain.
Okay.
Huntington.
Yeah, because I'm thinking maybe that like it is describing each evaluation domain at the different steps of the FFT, and then you finally get to this D1 over J, where and then another thing, I don't know what an orbit is. I only know about those in space. So it was definitely some fun math here. But if we go back quickly to the circle field, there was one thing. Okay, I just wanted to highlight that this is the curve of the circle, right? X squared plus y squared. So this is how we're defining the field. That was all I had for that slide. And then, so the circle friendly FFT. This is another one. So we're in the FFT, you break down the large polynomial into even powers and then odd powers. And then you basically evaluate and then break it down again. You call the FFT like recursively. So it kind of breaks the polynomial down into these, really digestible bits that can be used just like what we were talking about here, where you take this really large polynomial, and then after multiple rounds, you get a small one. And then that small one's evaluation is used to recursively solve the polynomials back up the tree until you can solve this large one very efficiently. So this is the circle FFT. This is a really high level overview. The math details are wicked. But this is the important part of the paper. This is the meat of the paper, which is the circle proof of proximity. So what the prover is going to do is basically create this this evaluation function over the domain, and then they're going to take this polynomial, and then they're going to create Merkle commitments to evaluations of it. And over time, what the verifier is going to do is take this lambda value and then use it as a, you could say, kind of an evaluation point. Say, hey, I want you to use this lambda value to create your evaluation points as you're coming up with this proof. Because basically, in order to make so we have interactive and non-interactive zero-knowledge proofs, right? So in order to make the FRI protocol non-interactive, the prover has to do all of the interaction itself. It has to kind of like talk to the verifier before it even talks to the verifier. So that's what this lambda value is for it to essentially do all of these steps of the FFT and then kind of generate the proof so that the verifier only has to do one of these small little leaves, and then that's what the commitments are. It's like the Merkle tree is the evaluations of the FFT. I could try drawing that if you all want me to, like kind of like draw a tree. I could try. So basically, all right. Let's say we have big polynomial, right? Big B for big, x to the 40, blah 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 blah, and then it goes all the way down to plus 6, right? What we can do is break this down into even and odd polynomials, where we get x to the 40 plus blah 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 blah, and then 6 is even, so it'll be like plus 6. And then odd one, so it'll be x to the 39 plus blah 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 plus something, let's say 7x, right? Because it's 7x to the 1, right? And then you basically call it again, and you create another. This is where the twiddle factors come in, because what you have to do is kind of map the polynomial onto a circle. Oh, there's actually a great diagram of this on the, it's not this exactly, it's not this one. It is,
What do you split it in the second time? If it's already split between even and odd?
oh, the second time, so they're going to be evaluated, right? But then in order to evaluate it, you take the even and odd indexes. These are just the indexes, right? So you take the first one again, x to the 40, but now it's not just like even and odd coefficients. You're just taking the even and odd placements in the polynomial.
Okay.
So it's like maybe like x plus 38.
But 38 will be next to
Wait,
it. So
38 is the next one, yeah.
So it will be 36.
38. And then this one will be 36.
Is that,
I think it will be 40 and then 36.
40 and then 36.
I think
should
so.
that be, 40 will become 20? The degree will be lower, right?
Divided, you think?
Yeah, I think so, because is that if that's an FFT?
I'm not 100% sure. I do think this would stay at 40 because you have 20 in here at some point, right? So you have x to the 20 at some point.
But each layer, the evaluation point, it will be different.
Yeah, exactly.
So so this one will be x. So here you can use x to square. So it will become x, another x 20, right?
So x to the 20 will replace x to the 40? Or will it be x to the
what
40
I mean,
plus?
so here,
The
you
index will be
use some
divided.
omega. If you omega, then it will be or just the x. Then
Mhm.
next will be x. This one then
X
it will
squared,
be
yeah.
20. So it go the way down. Then later it will be x.
Just x.
Yeah.
Okay, got you. Yeah, thank you, Harry.
And what happens with the odd numbers?
I think you
I
minus
think-
one them. You minus
you-
one
you-
and then
you
you
got-
say.
Okay.
Something like that.
Yeah.
Okay, you can.
Thank you. And
So this is just recursion step before
Mhm.
priority.
So this one would be something like x19.
No. It will be x, then x. You always need this even number.
Yeah. Wait, so then why does this one go to 20?
Just you divide the power every time by 2.
Okay.
Like, because you can create two components which essentially add up, but you add to random factors, and therefore they should never cancel out identically. I mean, I can also explain it on the spot. I just remember that you have some random points where you evaluate them, and then you split it into parts, therefore, which essentially you can check separately because they should still add up because you add some extra check on the side. And
Okay,
like, you just
yeah.
go down until you go to
You-
low
you
enough
keep
power.
it at the random.
And you can stop at X, you can stop a bit higher. I just don't remember what the next step is. Did it have to work?
Yeah, I think the next step is when you get to a low enough degree,
Yeah.
is that the verifier just
It's
verifies.
correction code, something like that. Then
Yeah. Oh, that was actually one
low
one
degree
step that I
polynomial. So
forgot.
you need to then check that it's low
Yeah.
degree polynomial, and you can actually stop not at X, but like a bit higher because you can still do it efficiently for other powers.
Yeah,
Sorry.
because the blow up happens actually when you do the memory trace, and then you apply the error correcting code, and then it blows it up into
Yeah.
the error correcting code, and then you interpolate that,
Yeah.
and then you have the tree of commitments.
Is this the low degree extension that happens early on in the start?
Yes, because we need to get to power of 2 to do our kind of proofs.
Mm-hmm.
I'm not an expert, sorry, I did have a year ago.
Yeah,
There is some
yeah.
good blog posts on that.
Yeah,
Generally,
yeah,
like
yeah.
Vitalik Klingon starts.
Yeah, I'm still going through something.
It's definitely great resources on it for sure.
Yeah, definitely.
Yeah. Okay.
I have a question on the proof of proximity.
Yes.
Like just going back, why, like, just intuitively, why do we care about? Like, why is that important? Like, why is that the thing that we're aiming for?
Okay, got you. Because you want to make sure that this is a valid memory trace, right? So you know, like the Fibonacci example,
Yeah.
you set up these constraint and transition polynomials to kind of describe what the what this curve should look like
Yeah,
when
yeah.
when
Yeah.
interpolated after the error correcting code is applied.
Okay.
So the test of proximity is basically, I want to prove that this person has generated a valid memory trace at the end of the day.
Right, and this is the example you brought at the very beginning, which is like the curve. Like
Exactly. That is the proof of
Right,
proximity,
right.
where we want a proof of
Mm.
proximity to this curve,
Yeah.
not to this red one.
And that's not unique to the circle part of the.
No, it's not. No,
That's
no,
just
no.
Like, that's just standard.
All the circle is doing is making it so that we could do this on Martian fields.
Mm.
That's it.
Mm.
On 32-bit fields.
Right.
And then that one change causes like a 1.4%. I mean 1.4 times speed up.
Mm.
So it's remarkable, but surprisingly simple. Yeah, and then this is the next phase of the protocol in the query phase, where the verifier is actually sampling the evaluations from these leaves over here. And then so I had some remaining questions, particularly about like the algebraic geometry, which I have like a lot of blanks in, and then also a little bit in the FFTs, where there were reasons why some curves couldn't be used because they aren't smooth enough, and I'm not sure what, after my research, I still couldn't come to like a conclusive reason as to, what makes a multiplicative group smooth or not. And then also, how do you map actually I kind of answered this a little bit later, but for example, you have a finite field element, but then you have a bivariate polynomial on the circle. So I think what elliptic curves do is they take the you take the x value and then the y value and then concatenate them together. But I'm still not quite sure about this, and I know that complex numbers are somehow used in this step, where they take complex numbers on the unit circle and then map them to the values that you use, for example, in the memory trace, just field elements, right? So I'm not sure how that works. And then there was a lot of mention about the trace vectors being orthogonal to error codes, but I'm trying to think spatially, and what I know as orthogonal, like how can something be orthogonal to error codes? That was something that I still wanted to do some more research on. But other than that, yeah, that was I just used these two papers. And yeah.
Is the circle thing used anywhere else? Like, or any other people? Has it been?
I think this is the first implementation of a circle, surprisingly. At least it was marketed as the first time that it's been done like this. I think mostly like lines of just, traditional finite fields where they wrap around, or elliptic curves, but not circles.
Right. Like, is it? What I'm trying to understand is like, is this like a moment where we pushed beyond the line in the sand kind of thing, and then now we're in a new world where we're experimenting with circles kind of thing? Like, that's what I'm trying to gauge. Or it's just like a truly like unique kind of like so matching this specific case. Like,
Yeah, I mean, I feel like the reason why they did it is to use this particular field, but I'm sure that, I mean, you just think of mathematics, I'm sure that there are so many more use cases of having a circular field that may not have been discovered yet. And I know the Stu Prover, just in the code so far, they're basically doing the same thing that they did in Stone in the first version. They're just using this new field. So it's like, I think this is the first implementation, and they're gonna push Stu out. But then there might be some other innovation that, you know, could be found useful for Circle.
I'm curious, like essentially this means that we'll soon see oval fields and other stuff, potentially square fields.
Maybe, yeah. Square fields, that's,
I mean, I don't know, it's just, or like three-dimensional fields. It seems
Yeah,
like before
exactly.
for Starks we only tried one-dimensional, like direct fields like Goldilocks, etc. But
Exactly.
essentially this means that we can try more complex.
Any of them.
Okay.
Yeah. I think the major bottleneck here is this math.
Okay.
You know, like where you're evaluating or you're translating the evaluation domain to the domain of the circle, and then performing the operations on it. Like it's some strong algebraic geometry that you know, I was just looking at it. I'm like, all right, how long will it take Lance to really grasp this?
And is this just unique to how Starks work, or will we see like can we see these kind of things in Starks too?
Only Starks use the FRI proof of proximity. I don't know, Zach. How do you think you like, for example, Planck would use?
Well, this depends on what you mean by Starks number, because if you so for Planck systems that use polynomial Kuhn schemes from error-corrected codes, then this is absolutely useful. But basically using Fry as a polynomial Kuhn scheme instead of as a degree check like in Starks. So like the Tonki 3 type stuff, for example. Then this stuff is extremely useful. But if the curve-based Starks, it's not useful because you can't really make security to curves out of 32-bit fields regressively. So
Is there like a set of criteria for the algebraic form for you to use? Like what makes a elliptic curve? You know what?
you have to. I believe as a result that basically, if you cannot, your prime can't go beyond a degree 4 extension field without substantial loss in security.
Okay,
Which means I think like 64-bit prime is about the best.
Is the smallest one?
Yeah, and also just even making curves over extension fields is just not is problematic because you don't have you lose the ability to create curve cycles, which means you can't do recursion. But yeah, for like I think that over the next 10 or so years, the future of ZKP is really going to be around error-corrected codes, schemes made out of them, where this kind of technique will be really useful.
Interesting. What would you say is the equivalent of error correcting codes to like KZG based commitments?
Well, it's error-corrected codes is like the where you're creating a polynomial Kuhn scheme by proving that that there's a
like the Hamming distance
exactly is small, whereas for the curves you're basically you're using the I guess you could the discrete logarithm problem the same way.
Okay,
Same
okay,
way.
got it.
And then you're so there's like the security primitives, and you're building up some high-level Kuhn scheme out of that.
Yeah.
So they're very different kind of techniques.
Okay, interesting. Thank you.
What circles means here for FFT are still circle means that there are two curves, right? Is that-
So it's still one curve. It's just that two variables are being used to define like the field, right? So you have the circle curve is x squared plus
I see.
y
So
squared.
that's why the bivariate.
Exactly, yeah,
Oh.
by variate polynomial. We're using x and y.
I see.
And then also the circle is useful because it was like, this isn't exactly what the diagram was, but they're talking about how the geometry of the circle is good for fast Fourier transforms. Because basically in FFTs, you're taking these like two evaluation points and then recursively breaking them down into a point where there's just 2 evaluation points that you need to figure out for the verifier. So the circle is kind of, I mean, the FFT is kind of based off the circle anyways. Like they did the unit circle. So they just use the field to maximize that one operation that's really important in the FRI protocol.
So does it like, have they mentioned anywhere about more dimensions than just a circle? Like going to 3 dimensions, 4 dimensions?
Complex plane, yes, but I don't think like spheres or higher dimensions.
There are multivariate polynomials. I will mention that in.
Like X and Y, but like we can X, Y, Z, and then we have 3 dimensions.
Yeah, I think INA, but it isn't, that doesn't relate it to the circle or curve. It's just the name is hypercube.
Okay, yeah, it's the Plonk, I think, right? Hyperplonk, hyper.
Yeah.
That's where I remember that from. Okay, but yeah. Fair.
I'll have more results in the coming weeks. Cool. Thank you all so much.